Hi folks, it's been a while and I apologize for that. This lecture we're going to be talking about hypothesis testing. So let's get into it. When we talk about hypothesis testing, specifically we're going to cover the differences between hypotheses and theories. We'll talk about the core logic of hypothesis testing. So what a null hypothesis is, what a research hypothesis is, how we use those, and what it means to accept or reject either of those hypotheses. Then we'll get into the procedure for hypothesis testing and all its steps. We'll talk about the differences between one-tailed and two-tailed hypotheses. That means I'll give you the definitions and we'll talk about some use cases. In addition to that, we'll talk about some controversy in hypothesis testing. Specifically, we're going to talk about the idea of marginal significance, and we'll talk about Bayesian inference. You should know that hypotheses and theories differ in a couple important ways. A hypothesis is just a proposed explanation for some observations or some phenomena. If I saw a person when I was looking outside and then I looked away and I looked back, I could hypothesize that that person was abducted by aliens. It's a hypothesis. Is it likely? Maybe not. I could further hypothesize that they were abducted by aliens that are so powerful they could hide any evidence of anything that they've done. And so I wouldn't be able to detect the aliens. It's still a hypothesis. A theory is a set of principles that kind of work together to explain phenomena. Oftentimes, hypotheses could be elevated to the level of theory if they've been tested over and over and over again and seem to hold up to all of those tests. Now, there's a distinction between any hypothesis and a testable hypothesis. The same thing for a theory. In order to be useful in science, we need a hypothesis or a theory to be testable. And a testable hypothesis is one that could possibly be proven wrong. In my example before, if I hypothesize that aliens that are super powerful, so powerful that they could hide any evidence of their existence, if I hypothesize that those aliens were the ones that were responsible for the person disappearing from my view between the first time I looked at them and the second time, that is not a testable hypothesis because there's no way that that hypothesis could be proven wrong. I've said that those aliens are so powerful they could basically do whatever they want and I wouldn't be able to know. Again, to be useful in science, hypotheses and theories need to be testable. Not all hypotheses and theories are testable. With respect to the core logic of hypothesis testing, I want to talk to you about the differences between a null hypothesis and a research or alternative hypothesis, as well as helping you to understand what it means to accept or reject one of those hypotheses. In hypothesis testing, we have research hypotheses that are paired with null hypotheses. The research hypothesis is a statement that we actually want to test. So I could say, for instance, that I think exercise reduces the anxiety of people. And I could test that by comparing people who exercise to those who do not, for example. But the statement that I'm testing is that exercise reduces anxiety. Typically, we're stating that there's something other than random variation that's responsible for how our data are distributed, or that groups of data differ on average, or even that variation in one variable might be linked to variation in another variable. The null hypothesis, on the other hand, is a complementary statement for the research hypothesis. Those two together should cover all options. So if the research statement is exercise reduces stress, then everything else would be, well, exercise doesn't reduce stress. This is an important point that people sometimes struggle with. If I were to say that people who exercise have different levels of anxiety from people who don't exercise, those two statements are complementary. But if I say that exercise reduces anxiety, It is not complementary if I only say that, well, no, exercise increases anxiety, because that leaves out the possibility that exercise doesn't really change anxiety. And so if I were to find a result that said exercise didn't really change the anxiety scores, I wouldn't have anything that I could do with that information. So we have pairs of hypotheses, a research statement, that is what we generally want to test, and a null hypothesis, which is the opposite statement, or rather the complementary statement. So if we're saying that there's something other than random variation that's responsible for how our data are distributed, the complementary statement would be that random variation is what's responsible for the distribution of our data. If we're saying that groups differ on average as our research hypothesis, then the null hypothesis would be that groups don't differ on average. And similarly, if we're saying that the variation in one variable is linked to variation in another, the complementary statement would be that variation in one variable is not linked to variation in another. We'll talk more about this when we get to one- and two-tailed hypotheses. I'd like to drive this point home, that the null and research hypotheses must be complementary to another. The reason that's the case is because we want to set up a test such that if we reject one explanation, we have to accept the other. And that is part of the core of how we do hypothesis testing. It's important to know that we can never really know if the hypothesis is true. Statistics can't tell us that. We can know using statistics how probable that particular explanation is. And so while we're saying that rejecting one hypothesis means accepting its complement, we're not saying that either one of those is true. What we are saying is that hypotheses that are really unlikely to be true should be rejected. If it is really improbable that exercise is reducing anxiety based on my data, then that hypothesis should be rejected. The formal procedure for testing a hypothesis has a few steps. The first step is to make sure that we restate our question as a paired set of research hypothesis and null hypothesis. And we want to phrase that in terms of populations, because generally when we're asking questions in statistics, we don't care too much about the particular sample. We want to know what's going to happen to the population that they represent. So first, we'll restate the question as a research hypothesis and null hypothesis about populations. Then we're going to figure out what the characteristics are of the distribution we're comparing it to. We'll then determine what our critical values are, or what the appropriate alpha level is, and we'll talk about those terms a little bit later. And we'll calculate some statistic and or its p-value. We'll talk about what that means a little bit later. But finally, we're going to have to make a decision based on what we've calculated and what our comparisons are. We'll make a decision to either reject or accept our hypotheses, and that will either be the null hypothesis that we're rejecting, or our research or alternative hypothesis. If we were thinking about restating our question, that's step one for our hypothesis testing. First, let's start with the question. If our question is that patients are anxious because they're not very physically active, so we're asking if physical activity is driving this anxiety in patients. Our research hypothesis would be, or could be, that physical activity reduces anxiety. And then if it were that research hypothesis, the null hypothesis is its complement. That covers every other outcome. Physical activity does not reduce anxiety. And so that means that physical activity could increase anxiety, or it could just not change anxiety at all. Next, we would have to figure out what the characteristics of our comparison distribution are. But we'd have to think about what the comparison distribution is. So we're saying that the distribution of anxiety scores is lower in samples of people who exercise. So what we're also saying then is that in comparison to those people who don't exercise, anxiety scores are lower for those who do. So our comparison distribution is the distribution of anxiety scores for people who do not exercise. Next, we have to figure out what our critical values will be for that comparison distribution, or what the alpha level is. Let's stick here for a moment. So each inferential statistical test, so those tests that try to tell us whether there is something other than random variation causing the distribution we see. Each one of those tests has some calculated value that we call a statistic. In the t-test, you have a t-statistic for ANOVA, or analysis of variance. You have F statistics, and for chi-square, you have chi-square statistics. There are lots and lots of different inferential statistical tests, and each of them have some statistic associated with them. So there are lots of these things. Those calculated statistics come from some distribution of possible values. In other words, each value that calculated statistic could take has some probability of occurring. Some statistical scores are less likely than others. We'll see some examples of that as we move forward, but a critical value is a statistic that has a probability that is just so rare that we believe it's unlikely to be found at random, all right? So that is a critical value is a score that a statistic can take that is extremely unlikely to be found at random. So if nothing else is going on, if nothing is driving the distribution of data we see, then those values are too rare to be probable. The alpha level, on the other hand, is, instead of thinking about a statistic itself, we think about, well, how rare is too rare? And we set some threshold. So an alpha level is a probability of occurrence that is so low that we're willing to say any associated data did not occur at random. There probably did not occur at random. I know this particular concept might be a little difficult for folks to grasp, so I'm just going to remind you that you can reach out to me. You can reach out to me over email. That will be the best way to reach out, and I will try to get you some clarity on this if this isn't clear here. Once we know what the comparison values are, either our critical values for our statistic or what our alpha value is for the probability of getting our particular data set, once we have those, then we're going to go ahead and calculate whatever relevant statistic. So if we're doing a t-test, we will calculate a t-value. If we're doing a chi-square test, we'll calculate a chi-square value. I know that for some of you, those terms may not be super familiar, and it's okay because you don't have to know what those are right now. We will deal with t-tests in this class, and so you'll know what that is by the end of this course. For now, we can treat this kind of like a magic box. So we know that we have a critical value that we're comparing our calculated statistic to. So we will calculate that statistic, and then we will make our comparison, or we will calculate that statistic, and then we'll figure out the probability of getting that statistic at random. That probability is also known as a p-value. So each statistic is associated with this p-value, and if you're using critical values to compare, you'll compare the statistic. If you're using your alpha level for comparison, then you will compare the p-value that you calculated, or rather the p-value associated with your statistic, with the alpha level that you set before. At any rate, what you're trying to do is see if the values that you got for your statistic or its associated probability, if those values are too rare to have occurred by chance alone, too improbable to have occurred by chance alone. So we have our critical values. We have calculated our statistics. We can compare our statistics to the critical value, or we can compare the associated probability, or p-value, with our alpha level. If we find that the calculated statistic is more extreme than those critical values, then we could reject the null hypothesis. Remember, the null hypothesis is saying there's probably nothing going on. Everything here could have occurred at random. And so if those calculated statistics are very extreme, then that means that they're very rare. It's unlikely they could have occurred by chance alone. We do a similar comparison with the p-value. Now, it's also important to understand that we either accept the null hypothesis if we've rejected our research hypothesis, or you can say you failed to reject the null hypothesis if you've rejected the research hypothesis. Some folks are concerned about how you phrase this because people are uncomfortable saying that they accept the null hypothesis because they don't truly believe that that's what's going on. But I encourage you to change the way you think about this, or shape the way you think about this way. You have two options for explanations. You have the explanation from your research hypothesis, and you have the explanation from your null hypothesis. At the end of the day, at the end of your analysis, your job is to say which one of those explanations best explains the data that you have in front of you. And so if we reject our null hypothesis, then we are accepting that the research hypothesis is the best explanation for the data you have, given your two options. If you reject your research hypothesis and accept the null hypothesis, you're accepting that the null hypothesis better explains the data you have than the research hypothesis. Either way, as we reject or accept our null and alternative hypotheses, you are saying which one of your explanations is most probable given your observations. We can kind of summarize this in a mathematical way, at least when we think about critical values. If our calculated statistic, in the case of the t-test, if our calculated statistic is greater than or equal to our critical value for t, we would reject our null hypothesis. If, on the other hand, the calculated statistic is less than the critical value, we would reject our research hypothesis. Now let's talk a little bit about one-tailed and two-tailed hypotheses. We'll define them, and then I want to give you some guidance on when to use them. A one-tailed hypothesis, for a research hypothesis, states that there is an effect or some sort of relationship among variables of interest, and that that effect or relationship is in a particular direction. On the other hand, a two-tailed hypothesis states that there's some effect or relationship, but it doesn't tell you anything about the direction of that difference. For example, I could say that I believe basketball players are faster runners than football players. I am giving a direction. I'm saying that football players and basketball players differ in how fast they run, and I'm saying that one of them runs faster than the other. Alternatively, I could give a two-tailed hypothesis where I say, I think that the running speeds between football players and basketball players are different. I'm not giving you a direction. I'm not saying who I think is faster. I may not have a reason to think one is faster than the other, but I might have a reason to think that there is some difference. As for when to use a one-tailed or two-tailed hypothesis, one-tailed hypotheses are generally hypotheses that we make when we have some good reason to believe that there is a difference in a particular direction or an effect in a particular direction. Two-tailed hypotheses, also known as non-directional hypotheses, we generally make those when we don't have a good reason to believe that there should be a difference in a particular direction. It doesn't mean that there won't be a difference in that direction. It just means that that's not what we're testing right now. We're just looking for a difference. It does have some implications for when we accept or reject our null hypotheses. If you look at the figure on the right, here we're looking at an example of the t-distribution, which is a normal distribution. And when we make a two-tailed hypothesis, Those orange areas under the curve represent our regions of rejection. Those are regions that are more extreme than some critical value. In this case, for our two-tailed hypothesis with 10 degrees of freedom, we are looking at critical t-values of 2.228 and negative 2.228. So if I have a t-score that I calculate, which is greater than 2.228 or less than negative 2.228, I would reject my null hypothesis. I would say that there is a difference. The area under those curves that's indicated by that orange, that area is equal to the probability of finding a value in that region. So if my alpha level was 5%, right? So I am willing to accept the risk that 5% of the time, when I say that there's a difference, that difference may not really be real. If I'm willing to accept that difference, which is a standard level of alpha in many scientific fields, then that alpha has to get split between both of those sides. So I have 2.5% on one side and 2.5% on the other side. On the other hand, if I make a one-tailed hypothesis, you can look at the figures to the left and in the middle. The one in the middle indicates a one-tailed hypothesis in a positive direction. So I'm saying that my focal group has a greater value on average than my comparison group. In that case, all of that alpha, all of that 5% of error that I'm willing to accept, all of that gets placed on the right side, right? And so my critical value, my t-value, is smaller. It is 1.812. In other words, it is easier for me to find a value that is more extreme than that because I'm only looking for values that are extreme in one direction. Similarly, if I look in the other direction, and just in that direction, I have a t-value, a critical value of negative 1.812. If you have trouble understanding what a one-tailed and two-tailed hypothesis is, and if you have any trouble in understanding what that means about your alpha level and your critical values, as well as your decisions about accepting or rejecting the null hypothesis, please make sure that you reach out to me. Okay, now let's talk a little bit about controversies in hypothesis testing. I am going to preempt this by telling you that controversies in statistics are rarely riveting unless you are a statistician yourself. But these two controversies in particular, I think, are meaningful or can be meaningful to folks who are not statisticians as well. And I'm going to try to explain that value. Let's start with the idea of marginal significance. To explain marginal significance, let's think about the figures that I showed you when we were talking about one-tailed and two-tailed tests, right? I explained that we would make a decision to reject our null hypothesis if the critical value, if the calculated value for our t-statistic in that case was more extreme than our critical value. And this marginal significance idea goes for one or two-tailed test. It doesn't matter which. Let's think about a one-tailed test for just a moment. Let's say I calculate a t-statistic for a one-tailed test, and I find that the probability of getting the value that I got, the calculated statistic that I got, the probability of that is greater than my alpha. I set my alpha at 0.05, which is pretty standard, but then I find a value that is 0.051. Well, that's pretty close to the 0.5 that I would need in order to say that this is significant. Some people call this marginal significance. It's the idea of being very close to a value that would be statistically significant. If we're going to adhere strictly to hypothesis testing procedure, marginal significance is not a thing. You either accept your null hypothesis or reject your null hypothesis. You accept your research hypothesis or you reject your research hypothesis. I don't find the term marginally significant to be particularly helpful. And oftentimes, depending on the publication you are submitting a paper to, they may or may not accept the terminology marginally significant. I can see some value if we think about our study design. Sometimes when you are, often when we're sampling, we get samples from the population that aren't perfectly representative of the population. And if we collect a larger sample, we may get a better picture of what the population looks like according to some metric. And so some people will use this idea of marginal significance to suggest that they should go and collect more data, that perhaps their data didn't properly represent the population. And if it did, then the results would be statistically significant. I will caution you, if your results are very close, if your p-value is close to your alpha value, but just too much for you to reject your null hypothesis, collecting more data does not guarantee that the p-value will shift in your direction. If you are sampling randomly, you may get values that bring you further away from a p-value that is significant. So again, I think this idea of marginal significance, while it is something that you will hear commonly used, I don't think it is a meaningful and helpful term. But this is a personal and ethical decision about whether or not to use that term. The last controversy I think is particularly interesting. This is the idea of Bayesian inference. So all the statistics that you learn in this class take a frequentist approach. And so frequentists calculate statistics, whether they are summary statistics like your mean, your median, your mode, your standard deviation, variance, so on and so forth. They calculate those based on what they observe, so the frequencies that they observe. And we do not influence our calculations, not explicitly anyway, based on our beliefs about the data. What do I mean by beliefs about the data? Well, I did mention before that when we sample, we get an imperfect picture of the population. If you have some reason to believe the population is different, let's say if we think about coins, if I think that a particular coin that I have has come from a population of coins that are biased, right, so that they tend to land on heads more than tails, then I expect a different set of results from a series of coin flips, right? Bayesian approaches to statistics take into account one's beliefs about the data explicitly into calculations of the mean, median, mode, or any of these inferential statistics. It's a pretty cool system, and there are a lot of ways where Bayesian inference makes a lot of sense. It allows us to try and make inferences in some cases that are difficult to make with frequentist approaches. And sometimes when we take a frequentist approach and a Bayesian approach to the same set of data, we may find different results. Not always. Most of the time, you're going to come to pretty similar results. But the idea of explicitly incorporating one's bias into your calculations is something that I think is interesting to me. Now, one thing that you need to remember is that both types of statistics are influenced by bias that is not accounted for in the calculations. statistics, although they are heavily reliant upon logic, are always done by humans, and therefore they are affected by those humans' biases, and that may be in how we collect our data. There's a famous example with a scientist, Samuel Morton, who was an anatomist and very interested in intelligence, but also had some very unsavory opinions unsavory in a modern context, unsavory opinions about who was smart and who was not smart. He was convinced of the impact of race on intelligence, and how he collected his data gave him a biased sample to start with. But in addition to having the biased sample to start with, how he cleaned his data to allow him to do analysis further reflected some of his biases. He would throw out throw out samples that would make individuals of particular races seem to be smarter. And he would include samples in other races that would make them seem dumber than they were. So this was not done explicitly, in the sense that Morton did not say, I'm removing these individuals because I think that they are less smart. This was an implicit bias that snuck into his work. And it's interesting as a case study because Morton published all of his data. And so one can take a look at the data that Morton published, as Stephen Jay Gould did, and the work he did for the mismeasure of man. You can take a look at the data and you can do the calculations yourself. You can see that there were some glaring mistakes that someone should have been aware of. It would not have mattered whether Morton used a Bayesian inference approach or a frequentist approach to calculate his statistics, because the biases that he was dealing with were implicit and things that he was unaware of, or at least unaware that he should be aware of. So no matter which approach we take to statistics, we need to be very sober about the fact that humans are the ones who are doing their statistical analyses, and therefore it is often worth it for us, particularly with controversial topics or topics that people have strong opinions about, to take a look at the data and have as sober as possible conversation or investigation into how these statistics were calculated. Okay. Okay, we covered a couple things in this particular lecture. There are going to be more things on hypothesis testing that we'll be covering next week. Just remember that hypothesis testing is a method for us to evaluate the relative plausibility of some competing hypotheses about the phenomena that we are observing. Hypotheses have to be testable in order for them to be useful in science, but not all hypotheses are testable. And formally, hypothesis testing has 5 steps to them. Restate the question as a research hypothesis and a null hypothesis about the population, determine the characteristics of the comparison distribution, and then determine the critical values or appropriate alpha level for that comparison distribution. And then we calculate our statistic and we make a comparison to those critical values or alpha levels. And based on that comparison, we finally decide to accept or reject the null hypothesis or the research hypothesis as being more plausible than the alternative. Those tests can be done in a way that is either one-tailed, where we have a direction in which we believe that a difference exists or that an influence exists, or they can be done in a two-tailed direction where we don't specify the direction that some influence or difference exists. We just say that it exists. In the next lecture, we'll talk more about hypothesis testing. We're going to talk about those errors that can be made when we're testing a hypothesis. So we're going to go back to the error that I mentioned before, where we are risking making an incorrect conclusion. There's actually 2 ways that we really think about making this incorrect conclusion. So we'll talk about those types of errors, type 1 and type 2 error. And then we'll talk about statistical power, or the ability to detect some effect that exists. We're going to talk about a concept called effect size, as well as statistical significance and a few other things in the next lecture. I hope this was helpful for you, but if anything is unclear, I'm going to remind you again, please just reach out. I am happy to help folks understand this. I think the world would be a much better place if we all had a solid understanding of how statistics work, and we put that to use.